Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a simple analysis of a gear system I found. This is a seed spreader. You crank the hand crank, that's the input angular motion, and this thing spins right here. This is the output angular motion. So, you're trying to broadcast the grass seed as far as possible. So we want this thing to spin fast. And, well, let's see. Let's count. I'm going to try to do one input rotation and count how many output rotations we get. You ready? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 rotations on the output for every 1 rotation of the input. It's hard to see the gear setup right here, but this is the input. That's connected to the hand crank. There's the first output. I think that's a 1:4 ratio. I think the output is 1/4 the input. So that means we need another gear ratio of 0.5 over here. I think there's another little bevel gear that's hidden that is half the size of this guy, giving us our 1:8 gear ratio. The speed multiplier. Gears have a very particular whine to them. And that's really what I want to talk about. The teeth and mesh, they interfere. That is, they have to have the same linear velocity or tangential velocity on the outside rim. And there are 2 mathematical ways to think about this. You can do angular velocity in radians per second multiplied by the radius of the circle. This is actually the opposite setup from my grass seed spreader. This is a big input wheel on a small output wheel. That gives you a gear ratio less than 1, 1/8 in my case. This is reversed. So if your input wheel is little and your output wheel is big, this is a torque multiplier. This output would spin more slowly than the input, the opposite of my seed spreader. Anyway, the trick is to realize that the rim, that is the meters per second at the teeth, has to be the same. So you set the 2 tangential velocities equal to each other, and here we go. For every 1 rotation of input, I add 8 rotations of output. That's a gear ratio of 1/8 or 0.125. Maybe you're not into radians. Get into radians. Do the dance, y'all. Here we go again. This arc length is a piece of the circumference of the circle, and my other arm is the radius of the circle. So if you divide the arc length by the radius, it's called a radian. It's a better way of saying angular displacement. Eventually, instead of saying 1/4 of a rotation is 90 degrees, you will say it is pi over 2 radians eventually, sooner or later. Well, if you're not there yet, this is maybe a more simple way of defining the 2 tangential velocities. So it's just distance over time. It's like speed equals distance over time, equation number 1. Except now it's a special distance. It's the circumference of the circle divided by the time for 1 rotation. It's called the period. So circumference is obviously 2 pi r divided by the period. Like I said, period is seconds per cycle, time for 1 rotation, but dividing by the period is the same thing as multiplying by frequency. Frequency is described as cycles per second, or hertz. All right, so frequency and period are inversely related. Dividing by the period is the same thing as multiplying by the frequency. And really, it's really the same outcome. So the input frequency divided by the output frequency, for every 1 cycle I put in to the hand crank, I got 8 cycles out on the paddle wheel. And like I said, I think it's a compound system. I think there's 1 gear ratio of 1/4 and a second gear ratio of 1/2, leading to a total gear ratio of 0.125. The exercise is just to figure out a spreadsheet that'll calculate the gear ratio, and then given any input angular velocity, it'll give you the output angular velocity. Given any input torque, it'll calculate the output torque. Pretty simple exercise. Anyway, find a set of gears somewhere in your house and make 2 simple measurements, and you can do all these fun calculations. Thanks for watching. See you in the next video.